Okay, welcome to our fifth section. This is the applications part. This is one of my favorite sections because what we're going to do now is we kind of assume that you now know how to take derivatives of pretty much all sorts of functions. Well, you should know how to derive polynomial functions, exponential and logarithmic functions, square root functions, trigonometric functions. You should know how to take derivatives of all your main sort of things. Now what we want to do is we want to start applying this. And I mean, this is, like I was saying here, this is why I kind of like this section, because now, hopefully after doing 4 units, we'll finally have some purpose behind it. We'll go, okay, I see why this is useful. Now, I can't promise that everything here you'll be like, oh, wow, this makes, I get this. But hopefully you'll agree, and I say this to my classes a lot, hopefully you'll agree that to someone, somewhere, you can see the applications. You go, okay, yeah, for an economist, I can see why this would be important. Or for an engineer, I can see why this would be important. I can't promise you that everywhere in your life you'll use this. When we talk about when will I ever use this in math, I can't promise you that. But hopefully you'll agree through the course of this section, you'll be able to say, okay, I can see how to someone, somewhere, this could be a useful thing to have. Which is one of the reasons why calculus is required for so many fields as like an introductory level course. Management students need to take it. Economics students need to take it. Obviously, the sciences, it's required as well. So, anyways, that's our goal, is to talk about where we can use this. There's 3 different kind of sections to our new unit here. There's a couple of actually quite short lessons. Like today's lesson and the next day's lesson are actually very, very brief. First thing we're going to do is we're going to talk about derivatives a little bit more, including what are called the higher order derivatives and their purposes. Then we're going to do a whole bunch of word problems. That'll be kind of the second section, where it's all just the word problems. And some kids love it, some kids hate it. Because the derivative part is usually really straightforward. It's usually an easy derivative. But the problem-solving part, well, what do I do where? How do I use this information? Some kids don't. Some kids aren't a big fan of that with word problems. The last thing we're going to do is we're going to show you how to use derivatives to sketch graphs, which maybe seems a little bit silly because we have computer technology which can sketch graphs, obviously, right? Your graphing calculator or some sort of online simulator can sketch a graph for you. But what I need for you guys to understand is that when it comes to curve sketching, your calculator is really just utilizing calculus to sketch this graph in order to find out some of these properties of it. And so to someone somewhere, the person who managed to program this calculator to use calculus to sketch this graph, it is important. We now bypass that section. We use a shortcut and we just say, well, let's just type it into the computer program. But again, this whole to someone somewhere, this matters. I need you guys to recognize that in order to build a lot of the technology that has been built, it's been based on this calculus. And now when you guys use your smartphones and you use some sort of app, or when you've got, I don't know, self-driving cars, whatever is happening here, right? We just kind of, I think that sometimes society, we forget that, the math behind this took a long time to be able to write the program, and that we can't forget all of the basics here and just say, the calculator finds me the answer, because really the calculator or the machine that finds you the answer, it's doing the calculus for you. So the person writing the program needs to know how it works. So anyways, I'm getting off track. Let's get started on our section. Today's is very short. It's known as higher order derivatives. And basically the concept is if we can find a first derivative, which often we'll write as, say, y prime or f prime x or dy over dx, well, why can't we take a derivative of a derivative? That's essentially what's happening, is you're taking a derivative of a derivative. And again, derivative. This is going to have more purpose as we move forward. Like the second or third derivative might mean something in a context. So that's why we're going to start with this before we get to our word problems, because sometimes when you solve something, you might not be looking for derivative 1, you might be looking for derivative 2 or 3. So the notation's pretty straightforward here. Often we'll write 2 little hashes next to y prime or 3 little hashes next to y prime. This notation here is the Leibniz version of the notation, where essentially you have dy over dx, and what you're being asked to do is take the derivative of that. The d over dx means take the derivative of a current derivative. And the way this notation kind of was developed then is that, see how you have d and then you have a second d? In a way you have like d squared with a y on top. And on the bottom, we don't write a bracket, but it's almost like you have dx all squared. That's kind of like how this notation is supposed to work, where this is the derivative of a derivative. That's kind of the shorthand notation. So let's give it a try here. We're going to find the second derivative of these functions. So, for example, if I did d over dx for x to the 6, this would mean that it is 6x to the 5. Right? That's the first derivative. That would be equal to y prime. Well, then if you want to find d squared y over dx squared, means you have to derive this 6x to the 5. So, well, let's not write it like that. This is what we would have done for the first one. We've already taken a derivative. Let's do the derivative of that's a better notation. D over dx for 6x to the 5 is going to give you 30x to the 4. There. We've now taken the second derivative. Right? Drop the 6 down in front, reduce the exponent to a 5, then drop the 5 down in front, make it a 30, reduce it down to a 4. So just derive and then derive again. So I'm erasing, by the way, because I need the space for the next ones. So if you need to rewatch that one, watch again, because this next one's a bit more challenging. If I want the derivative of 5x squared root x, we need a product rule. So we need the first times the derivative of the second plus the second times the derivative of the first, which means that for our first derivative, you're going to have 1/2 times 5x squared times x to the minus a half. And then for this next one right here, you're going to have 10x root x. Hopefully you can kind of follow how I'm doing that in my head. While I'm at it, I want to kind of clean this up a little bit because I have to take another derivative after this, so I want it to not be so annoying in terms of like how it fits together. So I'm going to make this 5 over 2, and this will be x to the 3 over 2. And then I'm going to make this 10, and lo and behold, this actually ends up being x to the 3 over 2 again. Which means that, let's see, that would be 20 over 2, so 5 and 20 would be 25 over 2 x to the 3 over 2. There is our first derivative. Which, now that I think about it, I could have done that a little bit sooner. This is x to the 4 over 2, that's x to the 1 over 2, which means I really had x to the 5 over 2. So pull the 5 over 2 down in front, you'd have 25 over 2, drop the exponent by 1, it's 3 over 2. Okay, so I guess I did it twice there. Once using kind of a combining exponents rule. Here I use the product rule. Now to find the second derivative, I need to derive this guy, right? So bring the exponent down in front, drop it by 1, gives me 75 over 4 x to the 1/2, which is 75 over 4 root x. There's our second derivative. This is really intuitive. Hopefully it makes a lot of sense. You're finding a derivative of a derivative. So, okay, one last time here. Let's deal with this last one here. This one is a chain rule. And the chain rule one becomes kind of challenging because you've got a baby inside that you're going to find the derivative of. And then you're going to have to do that again when you do the second derivative. All right, so first derivative. Pull the 10 down in front. 2 minus x squared, drop the exponent down to 9. Take the derivative of the baby inside, which gives you, oh goodness, 2 minus x squared to the 9. And then this guy's derivative is going to be minus 2x. So my final derivative of the first derivative is minus 20x, 2 minus x squared to the 9. There's my first derivative. There's not a lot of way for me to put this together any nicer. I mean, I could FOIL this out 9 times here, but that's horrible. That's not going to be fun. So I think I just need to use the product rule for my second derivative. So for my second derivative, let's go with the first times the derivative of the second plus the second times the derivative of the first. And I've been harping on this since the beginning of our derivative sections. Learn some good notational skills so that you can keep track of what's happening. There's not necessarily one right way of doing it, but hopefully you're able to follow and say, okay, look, I needed to take one extra derivative here for my chain rule. Now for my second derivative, I'm using this notation or maybe this notation. I mean, both of them are fine. The double one sometimes looks like an 11, which makes it kind of awkward. You could use the d squared y over dx squared notation, whereas like here you could just write dy over dx because we're only on derivative 1. But anyways, the point I want to make is find a notation that's going to be consistent and works for you so that you don't make a mistake and do something silly. Like, for example, right here, maybe you just would stop there and just say, okay, look, I'm done. But you need to remember, no, I need to take an extra chain rule here. So we need an extra chain rule of this. And, I mean, if you don't want to rewrite out the d over dx of this little bit here and just go right to the derivative, look, so long as you're comfortable, now might be the time to do it. Right? If you just wanted to throw a minus 2x on in the end there to chain on the extra chain rule, that's fine. But don't make mistakes because you're being sloppy and because you're trying to go too fast. So, all right, and then the derivative of this guy right here is minus 20. You might even see here, like, I need to make sure I'm really clear that's a times minus 20, not just a subtract 20, because now I'm going to want to clean this up a little bit. 20 times 9 is 180, times by 2 should be 360. So we should have 360x squared, because this x and this x will multiply by each other. You'll still have the minus 2x squared to the 8 left over. And then for the last little bit, you'll have minus 20 of a 2 minus x squared. One last thought, you could actually factor out a little bit of stuff. There's a 20 in both of these terms. There is also a single 2 minus x squared in both of these terms, which means that if you factor 20 out of 36, you should have 18x squared. 2 minus x squared. Now you factored 1 out of these guys, so there should be 7 of them left. And then you basically took all of this out of there, so there's a minus 1 left over. You could, I repeat, factor it back to this. The only reason this would be useful is if it's purposeful in your solving. For example, if you're being asked to solve for where this is equal to 0, well, now I can maybe see a little bit easier way of solving where it's equal to 0, because I could say, well, okay, where 2 minus x squared equals 0. I can solve for that as a factor. So, but it really depends on where you're going with this, what the context is. So I want to leave it there. The point of today is basically, can you take a derivative of a derivative? And if you can do that, then there's a few main notations, right? This is one of the notations, the one I'm just uncircling in the middle here. The d squared y over dx squared, that one's good. Double prime for y or double prime for x is also a good notation. I don't really care so long as you keep them straight, because what ends up happening, like you were seeing here, is that I'm going to be taking a derivative here and here and here. And so you got to keep track of where you still have more derivatives to take and where you're done taking derivatives. Don't write d squared y over dx squared like when you're taking this derivative here, because really you're taking them, say, one at a time. So just derive them each with one piece or section at a time. So that's more or less my lesson. It's a very basic intro kind of concept. So if you'd like to, you probably could take the time right now and even move on to video number 2, because the first 2 videos kind of go in sequence where we want to kind of build our way into some word problems. So anyways, I'll leave it there. The next topic is where we do some applications of these derivatives now, where you want to find either the first or maybe even second derivative. So, okay.